So it's simple, guys. Like, what are the changes you do in the output that should be back propagated to input, and input should be forward propagated to output, like vice versa thing. Because independent and dependent variable came altogether. So that, like that, only this back propagation losses gradient should be propagated back to find the input or initial weights. These are the back propagated things. Like output back propagation should be passed to the initial gradient, so that we can recalculate this, because the changes have happened in the output side. So that should be back propagated to calculate the new gradient or actual gradient of in the initial side. Let's see a simple diagram of back propagation through time, how it elapses. So we have just found the total loss. So L1 loss here, L2 loss, LT loss. So these are the sequences at t is equal to 1 or 0. We can say t is equal to 1, t is equal to t minus 1, anything, or 1 means t. So here we will get dl1 by dy1 as we have seen earlier. Now this is y1 output, so this is output and this is input. So with respect output and with respect to input, simple gradient how we will do that is back propagated throughout, and to find this we will use that as vice versa, as I said. So here we will be having dy1 by dh1 input output, and that if we want to calculate like dl by dw, then again these things are useful. dh by dw, dh is nothing but we will get the dw, so dh1 by dw we will get over here, as I've showed over here. dl by dy1 over here, we are just finding this. Then dy by dz, dy by dh, because z is nothing but vht, so we can just keep h also. And then dz by dv, that is nothing but dh1 by dw. So this is for just first timestamp, t is equal to 0 or t is equal to 1. Let me keep t is equal to 1 only, so that it will be matching with input. So t is equal to 1, we will just flow goes from like this, and it will back propagate here also. This is u that we'll see. For now it's just back propagating like this, so till here it's reached. But for timestamp 2, what happens is like we will get dl2 by dy2, then dy2 by dh2, output input gradient, and then over here dh2 by dh1, we will see how this will calculate or solve. And then here we again get dh1 by dw for this flow. That flow goes something like this, as you can see this line. It goes here like this, and it again can go like this also, as it went. So this is back propagation through time, as you can see. And this is like something linear, again back propagation through time only. But here this is which is interesting. So for h2 it will calculate it till here, and it also goes to previous timestamp also. For h3 again it will go something like this. For h3 all the h3 parameters will be there, and h2s, and then h1. L4 parameters will be there, L3s, h3s, h2s, and h1s. It will back propagate through time. So back propagation happens from current state to previous stages till L1, like initial timestamp. So now what happens is like we need to calculate and solve these gradients also for telling you how back propagation through time happens. So we'll just see for how we can find dl2 by dw, so that you can get an initial idea. So we can just write this as dl2 by dy2, as you have seen, and then dy2 by dh2, this one, and then dh2 with respect to w, right? dh2 with respect to w, because here we also have what we can say w, right? So we can just calculate dh2 by w also over here, because h2 is the output with respect to input tw. So this is also there. So we are just categorizing this thing here, and again by chain rule we get dl2 by dw. Now how we'll solve this, we will see next. Now you might already guess that how we'll calculate dh2 by dw. So because in h2 equation, tan h of ux2 plus wh1, we have h1. h1 here it's not a constant. h1 is again in itself a term. If you want to show like what h1 is, like nothing but h1 is equal to tan h of